So, welcome to lecture number 3 of this Mechatronics. We have conducted 2 lectures and they have been uploaded in YouTube channel. You can see it later on. Okay, so this lecture also I am going to record due to electricity problem. I am going to wind up this lecture within 10 or 20 minutes. Okay, so today. Okay, my screen is visible.
Yes, sir.
Okay, no problem. So I'm Professor Sachin Tolkar, Navasayada Education Society. This is unit number 1, Introduction to Sensor and Actuator. We have seen in first 2 lectures some sensors. Now in this third lecture, we are going to see temperature sensors or thermal sensors. The objective of this lecture is, at the end of this lecture, we all should be able to understand various kinds of temperature sensors and working principle of the temperature sensor. Both. Uh, this part, echo generator, we have seen in last lecture. Temperature sensor is an important parameter in many control systems because in mechanical as well as automobile system, we need to detect the temperatures. Several distinctly different transduction mechanisms are employed. These include non-electric as well as electric methods. In mechatronics, we are going to consider all type of non-electric and electric methods to calculate temperature. Thermometer is our most common non-electric sensor. Common electrical sensors include thermocouple, thermistors, and resistance thermometers. These 3 we are going to study because thermometer we know we have studied in your thermal engineering. Temperature transducer can be divided into 4 main categories. One is RTD, that is called as resistance temperature detector. So it will work on resistance principle. Second one, thermocouple. The range are like this. For RTD is minus 200 degrees Celsius to 650 degrees Celsius. For thermocouples, it's about 650 degrees Celsius. Thermistors are used for minus 100 degrees Celsius to 300 degrees Celsius. Now, what is resistance temperature detector that we are going to see? As temperature changes, resistance of material is also changing. So, resistance is directly proportional to um, resistance. The resistance of conductor usually increases as temperature increases. So if temperature increases, resistance also increases. If the properties of that conductor are unknown, the temperature can be calculated from the measured resistance. This is the basic principle of RTD. And in this case, we can use any conductor, but a few have been identified as having more described characteristics than others. So some metals will give you, or some conductors will give you perfect analysis of your temperature detection, and that's why the characteristics which are desired include the relation between temperature can be calculated from the equation. Okay, the equation is missing here, but I'll post in next. I'll just admit some people. They are coming. Admit all. Okay. Okay. They have been admitted. Now, resistance temperature detection or detectors will be employed with the help of some specific conductor. Just now I have told you that conductors are platinum, nickel, or resistor wire elements whose resistance variation with temperature has high intrinsic accuracy. We need accuracy in temperature detection. That's why platinum and nickel will be used. They are available in many configuration and sizes. as shielded or open units of both immersion and surface application. So sometimes surface application will be there. Sometimes we can deep that particular RTD sensor in that material. So RTD connections, it is a bridge circuit. With the help of bridge circuit, we know that bridge circuit we have applied in various elements. So bridge circuit is commonly used to detect the temperature difference, this resistance differential with the help of fourth leg. So these three legs will be balancing each other. These three legs are used for balancing of resistance, and fourth leg will show you actual change in resistance. And we know that the resistance changes, the temperature changes. So resistance and temperature both are having linear property, and that's why we use these this copper, nickel, and platinum in RTD sensors, RTD detections. Now, second type is called as thermistor. Thermistor, it is a electrical resistance for most material changes with temperature, and by choosing material that are very sensitive to temperature, we can make devices that are useful in temperature control circuit as well as temperature measurement. Okay, a thermistor is a semiconductor. It is sintered mixture of metallic oxide. So these are the some you can say disk type, rod type, or bit type thermistors they have been employed. So it may be a metallic oxide mixture, a sintering, such as oxides of material of cobalt, copper, uranium. Thermistors have a negative temperature coefficient. That is, the resistance decreases as their temperature rises. This is somewhat different than your first RTD, because in RTD resistance temperature detector we have seen that there is a linear motion or linear you can say a relation between temperature and resistance. In this case, thermistors, we have negative temperature coefficient due to their configuration, and the thermistors are extremely sensitive but over a narrow range of temperature. The temperature range is very slow, you can say low. The resistance temperature relation is known to follow the law RT is equal to R0. R0 is initial resistance, E raised to beta into bracket 1 upon T minus 1 upon initial temperature T0. So it is having, you can say, it is having a relation like this, which is negative temperature coefficient. Here, constant and all temperatures in Kelvin, T0 is the ice point temperature and R0 is the corresponding resistance to the thermistor. These are the types of thermistors which we have shown in diagram. Disk type thermistor or rod type thermistor, and third is bit type thermistor. Next. Now third, that is thermocouple. One of the most commonly used methods of measuring temperature in science and industry depends on the thermocouple effect. So thermocouple effect, we know it is a Seebeck effect. If there are two junctions, one is put at cold and one is put at hot, then there will be change in voltage. And if the temperature difference is producing voltage difference, if we can calculate that voltage, uh, here electricity is not there, so my laptop is running low, but we'll conclude within 5 minutes. It will help. I think it will give us that much backup. So there is change in voltage, and that voltage, if we can calculate, then we can calculate the temperature differential also. This is called as Seebeck effect. The diagram itself is self-explanatory. The magnitude of thermal EMF depends on wire material used on the temperature difference between the junctions. So one junction will be put at cold and one junction will be put at hot, and we'll get the voltage differential in that particular thermocouple material. These are some thermocouples, just like iron constant, positive wire and negative wire combinations will be there. So iron constant, chromal aluminum, copper constant, and chromal constant. Okay, somebody's mic is on and that music is very pleasant, but still, please mute your mic. Okay, so these are temperature ranges for iron constant, chromal aluminum, copper constant, and chromal constant. Normally, we see that negative wire is having constant in common lots of the time. So these are the grades J, K, T, and E. You may be having some questions on this because your second semester exam will be also on online basis. So you have to remember this table thoroughly. Now the last one, that is pyrometry. Maybe those who are working right now in or they have worked in uh, companies, they know that pyrometry is very much famous right now in forging industry. In pyrometry, there will be no direct connection of that thermocouple or thermoelectric part with that particular um, heat element.